Okay, so I think we're back with another problem to solve. So hello and welcome. Hope you're all doing well. Let's see, make sure I have I hope you're all doing well. Dreams, dreams, dreams. Boom, boom, boom. Boom, 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 boom. Yes, so here we are. Okay, let's go next problem. Let's get right into it. Just kind of making sure I have everything set up. Okay, anyway. Number of connected components in undirected graph. Go. This, I think, it's an interesting question. I think I've seen this before, although n nodes labeled from 0 to n minus 1 and a list of undirected edges. Each edge is a pair of nodes. Write a function to define the number of connected components in undirected graph. So, how many nodes do we have? All edges are undirected. Doesn't say how many. No duplicate edges appear. Oh, interesting. Okay, so this kind of should be easy question. Should be an easy question. The only problem I have is, well, we have to visit every node anyway. Yeah. Okay, never mind. So we should be fine. All right, we'll do it this way. Alrighty, ready for this? Use a vector, and I think that's all we need. We're not going to modify this. Oh, we also want a, actually, wait a second. It's n to 0, 1, n to minus 1. Okay, we only need vectors then. All right, let me show you how to do this. I'll explain it afterwards. So first, we want to build neighbor sets, or neighbor lists, or yeah, neighbor lists, or neighbor vectors. So we're going to have standard vector of int, standard vector int, neighbors, and we're going to say for int I, it's actually going to be edges, yeah. Edge. Okay, we'll do it this way. I edges of I, or yeah, edges.size. And we're going to say for int j equals. It's kind of confusing. Vector of edges of I. I'm sorry, never mind. Oh, I see what this is. Never mind. No. I'm doing it wrong. There we go. Okay, I was kind of wondering. I was like, why isn't this? Something doesn't seem right. A equals v of 0, b equals v of 1. We're going to say neighbors of, now we want this to be, n empty vectors. Right? We're going to say neighbors of A dot push back B, and neighbors of B push back A. All right, so we just want to be able to quickly generate our neighbor set, and we're going to say standard vector of booleans. We're going to say visited, and that's going to be n false. Okay, it's just an alarm. So we're going to have auto DFS. So what's going to happen as I'm programming this is we want to we're going to use a depth first search to traverse the entire graph. And what's going to happen is each time you traverse the graph, you're going to mark a node as visited. And the way it works is each connected component, we traverse the whole graph for that component, and you mark off all those nodes, and you increment your count by 1, you're going to look at the next node in the list, and that'll take you to another part of the graph, and then you're going to traverse that whole part and mark off all of those nodes as well. And that's the basic idea. Just a simple search, graph search, should do the trick. I think we want recursive graph search. We'll do. Can even do a breadth first search too, but I like depth first search. That's fine. So we can do we want int which node, right? That's really all we need. And that's it. That's the idea. Super simple. Super simple. So base case, base cases, I guess. If visited of which, then return. And we'll say visited of which equals true. And you're going to visit the neighbor set. You recurse inside in the neighbor set. So you say for auto x or neighbor or n in, let's not do n, let's do x. Neighbors of which, say if not visited of which, then DFS on x with, it's really f, it should be. And it's actually really simple, this algorithm. Like this literally just visits every node and marks them. And each time we call the DFS, we increment the count. So we DFS once on one of these nodes. And I want to say, I don't think we do anything more than that. I think it's that simple. It's just every neighbor that we haven't visited yet, we visit those neighbors. And we do need to do one small thing, which is just the parent. Make sure we don't go back to the parent. But the parent we end up visiting anyway, so it really doesn't matter. Yeah, it's visited immediately, so anyway. I think it's that simple. I don't know, what do we get if we do this? Let's compile. Wrong answer, nice. Perfect. No kidding. Really? Count to 0. Oh, that's why. I'm sorry. It should be X there. But it really shouldn't matter. I don't know if that should matter. Why did that shouldn't matter? Well, I think we'll go for it in a moment. Why wouldn't that matter? You really could and or should be able to just do all of these. Right? Like it shouldn't matter at all. Yeah, how come? Huh. But anyway, I like to just put that in there so it's just kind of an extra layer. Whatever, we'll just, kind of an extra layer, because you can put it in the base case or you can put it in here. Let's look at, yeah, it's weird. But anyway, let's see, what are there? 0 to n minus 1. Can we do one node? Empty. Can we do 2 nodes? Can we do 0 nodes? Should we get some kind of an error? Oh no, it works for all of them. Really? Wow. No kidding. I want to go for it. Hey, you got there. Sweet. It's relatively efficient. Uses a little more memory than most, but that wasn't too bad. How do we do? 10 minutes? I'll take it. Is that right? 10 minutes? Yeah, not bad. Not bad. Hopefully that was simple enough. This also could be done with a breadth first search too. All right, we'll end the stream there. Super quick. Super quick. Thank you for watching.